Good afternoon, everyone. We are going to learn now moment distribution method. This method was developed by Hardy Cross in 1924. Widely used method for analysis of structures uh, from 1930 to 1970s. Still, the availability of the computer-oriented matrix methods. Nonetheless, moment distribution method is still preferred by many engineers for analyzing smaller structures since it provides better insight into behavior of structures. It may also be used for preliminary design as well as for checking of the results which are given by the computers and using computer methods. It is popular due to its ability to solve the equations iteratively. Now, before we proceed for understanding the method completely, we have to understand some definitions and terminology. First thing is sign conventions. All counterclockwise moments in the members and are considered as positive. All clockwise moments on joints are considered as positive. Now member stiffness. Now consider one beam where one support is hinge and other support is fixed. So this moment is applied in anti-clockwise direction and there is a rotation over here. We are again going to use the slope deflection equations which are MAB and MBA. Let's call MAB as your moment M and theta A as your theta, and using this slope deflection equations MAB, where you are putting theta B is 0 because of fixed end, there is no support settlements and there is no loading, so we can consider all these three quantities as 0, and we can write that from this equation that M is equal to 4EI by theta, 4EI by L into theta. So to get the stiffness of this equation, you know that you have to apply unit rotation and you get the stiffness of this particular equation is 4EI by L, and which is called as bending stiffness. Now we can also calculate the new term which is relative bending stiffness, that you divide this bending stiffness divide by 4E and it gives you I by L. Now consider the second case where beam, the other support is hinge and both ends are hinge. You can use a second slope deflection equation where you can see here the MBA is 0 because of the hinge support, and the applied moment is still acting here at M, which produces the rotation. Now in this case what will happen? We use the second slope deflection equation. You can make the moment MBA 0 and the remaining quantities which are not known to us, keep it as it is, theta and theta B, and keep the settlement and fixed moment support 0. In this process you are going to get theta A is equal to minus 2 theta B. We write equation in the form of theta B is equal to minus theta A by 2. We substitute this equation into the equation of the moment over here using slope deflection equation, that is MAB is equal to M is equal to 2EI by L, and instead of theta B we are substituting minus theta A by 2, and from this we can see M is equal to 3EI by L into theta A. Now you know that theta A is equal to theta. So when your support, far end support here at B is hinge, you are going to get the applied moment is equal to 3I by L into theta. Now we can calculate the carryover moment. What is carryover moment? If the moment acting at support A, then what is the moment at the far end, that is at support B. So MBA in first case can be calculated by substituting In first case means where the far support is fixed, you are writing theta by 0 and remaining all quantity 0. You are going to get mb is equal to 2ei by l into theta. From this we can actually mba, you can substitute theta from the first equation, that is for the slope deflection equation we have obtained theta m is equal to 4ei by l into theta. From that we can write theta is equal to ml by 4ei, and that theta was nothing but theta a in that equation also. So we can substitute theta is equal to ml by 4ei into this equation, and we are going to get the far end moment, that is mba is equal to m by 8. So what are we going to achieve here? We are going to relate actually the far end moment mba and the applied moment. That is this is a moment applied at A and this is a far end moment at B. So you can see exactly the applied moment and the half is your far end. And in the second case, when the far end is hinged, obviously MBA is equal to 0. Now distribution factor. What is distribution factors? To understand this terminology, we can simply take this frame and where two supports are fixed and one is hinged, and there is a applied moment at this particular joint. Now this joint is rigid, it will be subjected to rotation theta, and you know that in all three members, this because this is rigidly connected joint, the theta remains same in all the members. The value of theta is uniquely defined over here. That means a let's say b, theta b for AB, theta b for CB, theta b for DB remain same. It is not different. So we write simply the free body diagram of joint equilibrium equation here. The member forces are also shown. So we are writing joint equilibrium equation here. M is plus MBA is equal plus MBC plus MBD is equal to 0, and like we are writing M is equal to, this is applied moment and these are the member end moments but acting at the joint. So we can separately write MBA, MBC and MBD, the member end moments, according to our equation, as because far end is fixed here, both cases we are writing 4ei by L and 4ei by L. For this third last member, because the far end is in, we can write 3ei by L, because this is a relation between MBA, the moment where we are applying moment. Here we are going to write moment equation here at this particular joint, and then we are relating it with theta using our own known equation. So substituting this into this equation, we are going to get this, and M is equal to, we can write in the form of bending stiffness, and then we can write the same equation in the form of relative bending stiffness as well. So if we take out this minus 4e outside, we can get in the bracket the relative bending stiffness. Just now we have defined it, and we can write so that here kb we can simply write from this equation, we can get theta. This theta is being substituted into equation 3 which was shown earlier, individual basically the moments, and we are going to get the relation between this M and the member moments. So what is this? Actually from this equation it turns out to be, this is sigma kb and this is kba. So what is MBA? It is minus kba divided by sigma kb into M. What is kba divided by sigma k? This is called as distribution factor. Now what is distribution factor? It is where we want to, in that particular member, how much moment is distributed in that member because of applied moment M, how much of M is distributed in the member BA, how much of M is distributed in member BC, how much of M is distributed in member BC. So this is called distribution factor, and this is nothing but bending, relative bending stiffness of that member divided by total stiffness of the relative bending stiffness, summation of that merging at that joint. Let's say MBA, if some other three members are acting, uh, for example in this diagram, if at this joint BA is 1 but BC and BD is all also joining, so at this joint the total stiffness will be from all, so relative bending stiffness because of all the members merging at that particular joint. We'll see more later this when we are solving the beam examples. This is just to give you an idea how distribution factor helps in distributing the applied moment among the members. Now you can also determine basically the distribution factor. If let's consider the applied moment as 150 kilonewton into meter. First step is to calculate distribution factor according to our definition. We are calculating, writing the distribution factor equation. We are getting the distribution ratios, and this we substitute into the our member and moment equations. We are able to get, okay, how much is a member and moment distributed because of M. So this you have to remember because this is the first step of the analysis. Now what is the actual process of moment distribution method? The basically in this beam you can see the joint B and joint C are going to have rotations. Now in moment distribution method, initially we assume that these two joints which are actually undergoing rotations have imaginary clamps. That means we assume that these joints are fixed. In my next diagram I will show you more clearly. The entire process says that we are going to actually fix these two joints, imaginary clamp of the joint which are undergoing rotation, that in the present case it is B and C. Now of course there are fixed end moments. We are going to calculate fixed end moments at every joint. Here this is fixed, here this is fixed, but here actually in real beam it is not fixed. So basically there will be unbalanced moments which, because these joints are not under equilibrium, it has not reached true equilibrium because of the imaginary clamp we are applying over here. So these imaginary clamp later on we are going to allow rotation of one of the joints one by one. That means first we release this joint, and whatever unbalanced moments because of the rotations this will undergo, because of course earlier it was fixed, now we are allowing rotation. That means there will be moment generated which is unbalanced moment. Now what is unbalanced moment? In first case it is, if it is minus 60 fixed end moment, if we are allowing rotation it is plus 60, because we have to allow, this is fixed end moment, but we have to allow the joint rotation of C. First we will release this joint, and later on, and then we have to try to balance this joint, because this is unbalanced joint, it has not reached true equilibrium, this joint is not under equilibrium. So how to distribute, how to make this joint under equilibrium and balance this moment, that we actually distribute these moments